Having some issues with the pen. Now, this is question 20 in exercise 6H. The question gives you a distance to another plane. They give you a plane equation, 2x minus y plus 2z equals 5. They tell you that there's two planes that are a distance of 2 units from this plane. Now, the reason why there's two planes is because these are parallel planes. I've written parallel there. Just like if you had lines, so they give you this line, and you say, all right, well, there's another line 2 units apart, but there would be a third line, right, if these were all parallel to each other. Okay, so really there's like, if I call this plane 1, call that P1, there's a plane 2 and a plane 3. Right, so the same thing with planes. Right, so they're giving me this one P1. There's some distance there to P2, but then there could be a P3 underneath that's also parallel. Right, and it's the same distance. The good thing about these being parallel is that we know most of the equation. Right, so in order for these to be parallel, it's only this constant value that will change. So it'll be 2x, it'll be minus y plus 2z. That will all be the same, but it will now equal some constant value d. Now just maybe to avoid confusion, I should make it a different letter, like a k or something. Is some value in that. Then we'll end up with this situation here. The other good thing about parallel planes or parallel lines is the distance is always the same between them, or the shortest distance. So just the line. Think about the lines. I could find a distance there, but I could find a distance here. As long as it's the shortest perpendicular distance, it's always the same. So I get to choose some point on one of the planes, and it can be any point, right? So what I'm going to do in this question is choose a point on plane 1, which I have to use plane 1. That's what I've got the equation for. And it can be any. So an arbitrary point almost. All right, just write choose a point. So P, I guess. I've drawn a little diagram because we're using the same formula we were using the previous questions. Point P on plane P1. You might want to make things zeros to make your life easier. Basically, any combination of numbers that makes this equation true. I'm seeing a 2, a 1, and a 2. I can make a 5. But that's negative. What if we did 4, 6, minus, yeah. So what about this point? 2, 1, 1. That will work. So if x is 2, that will be 4, minus 1 is 3, plus 2, because the z value is 1, equals 5. So that's a point. Maybe another point. Maybe it was easier if I could make the x 0 and the z 0. Then the y would have to be minus 5. Maybe that's an easier point to work with. As long as it satisfies this equation, I'll just stick with my first one. Right, because the planes are parallel, so you can go from any point. Now, in terms of using this formula, we're getting our normal from the second plane, we're getting our d from the second plane, we're getting our x1, y1 and z1 from the first plane, right? So I've tried to draw a little diagram. So it's like this is plane 2 or plane 3 with the A, B, C, and in this case it's going to be a minus k for D. And the point, the x1, y1, z1 comes from the first plane, and I've chosen this point 2, 1, 1. So I'll go to the formula. We're going to be also got a normal that we can see from our second plane. So this implies that the normal vector, getting that from the second plane, 2, minus 1, 2, right? And the D value that I'll need to fit in, so comma, would have to be a minus k. And the reason why it's minus k and not positive k is because when we derived this distance formula, our plane equation, I've written it here, was ax plus by plus cz plus d equals 0, not the x plus y plus z equals d. Right, so we used the plane equation in that form to get this formula. Right? So you're going to have to put your plane equation into that form, which means the k comes over here and it's now minus k. So I'm going to figure that out. We've got the a value being 2 times the x1 value being 2. So I've got 2 times 2 plus, all right, I've got negative 1, that's the b value. The y1 here is 1, that's easy, so this will just all be minus 1, then plus the c value is a 2, right, the z1 value is a 1, and the d that I'm using, I've decided to use the letter k. The magnitude of this normal is, we've got 414, so that'll be the square root of 9. And we know the answer, we know the distance is 2. So let's tidy it up. What have we got on top? In the numerator, I've got 4 minus 1, that's 3, plus 2 is 5. So I get the modulus of 5 minus k equals 6. All right, so square root 9 is 3. 3 times 2, to tidy this thing up, is 6. Now, when you've got modulus of some function, this is a very simple function, but just, you guys, I don't think I've done much modulus. If you've got modulus of some function equal to something, or, you know, or whatever, just the modulus of the function, there's two possible situations. Either the function is already greater than 0, in which case you can just get rid of the modulus altogether and just say I've got my function. But if the function is giving negative numbers, right, so it's giving negative answers, it's smaller than 0, then you have to make the answer positive, right? Now you've got to be a bit careful. You don't, say you've got some function like minus, plus, whatever, I don't know, that could be whatever's going on in the function. You're not changing every individual thing necessarily. I mean, here it'll probably work, but what if I times it by something? Like, you're not, what you should really do strictly is compute the function and then take the answer and make it positive, right? So how are you going to make something that's negative positive? You're going to times it by minus 1, right? So you compute the function, you get your negative answer, then you times that negative answer by minus 1, and now it will be positive, right? So I'll show that in the working. Here it's very simple, and I'm probably laboring on the point a bit too much, but we do have a function, I guess. It's 5 minus k. It's not just some number like it has been so far. So if the 5 minus k gave us something positive, right, then we could say, we'll go this way. So if positive, all right, positive, positive, then 5 minus k is fine, and it will equal 6, and we could work out that the k would have to be minus 1, and therefore I could put it into the plane equation, and I would get 2x minus y plus 2z is minus 1. So there's one solution. But if the k is, sorry, not the k, if the 5 minus k was negative, then what you would do is you'd take your 5 minus k, you would times the whole thing by minus 1, all right, so it's negative inside here, but you make it positive by doing this, by timesing the answer to that by minus 1. So what do we get? We'll get k minus 5 equals 6, and therefore k is 11, and if k is 11, I've got another plane equation, which is 2x minus y plus 2z equals 11. So I thought I'd do that question just because of the, you know, trying to work inside of a modulus here, slightly different, still fairly straightforward. The book tells you that you're going to get two planes, but if it didn't, then hopefully you would realize from the start that you could, because if you've got parallel planes, you could have one above or you could have one below, and you need those two answers. All right, done.